Good day, everyone. Welcome back once again. We're going to be looking today at finishing off the polynomials unit by learning about what's called a difference of squares. And this lesson can be found on page 15 of the West Country Outreach Unit handout. Very minor typing mistake at the top of page 15. On your handout, I believe it says 10.5.3. It should say 10.5.4. Not that it's a big deal, but a couple of you are using the textbook as an added resource, and the numbers at the top here, 10.5.4, refer to section 5.4 in the textbook. So what are we doing today? We're looking at ultimately factoring what's called a difference of squares. And because we have different methods of factoring, you have to be able to recognize what a difference of squares is in order to successfully factor it. And we're going to start by reviewing all of those different methods of factoring. We've learned how to factor a greatest common factor out of a polynomial. Sometimes I will use the word extract a greatest common factor. And in speaking with many of you over the past few days and looking at your work, I think that most of you have a really good handle on that. Factoring by grouping is always a little bit iffy, but that is where you have four terms and you group them into two groups of two. And using greatest common factors from each pair, you're able to come up with a factorization of the four terms in total. You've learned how to factor what I call simple quadratic trinomials, where we have 1x squared plus a number times x plus a number. And in speaking with many of you over the past few days and looking at your work, you guys are really, really good at that. What becomes a little more challenging for some students is how to factor when you have a complex quadratic trinomial where it's some number times x squared plus some number times x plus some number, where the number in front of x squared is not 1. And that involves using the method of decomposition, which really involves using grouping. And all I would say to you is the same thing I've tried to tell you throughout this unit. You have to persevere. You have to keep trying more and more of them, and sooner or later it's going to click. So what am I saying today? There's one more method of factoring, which is called a difference of squares. And in order to learn what a difference of squares is and how to factor it, we're going to be warming up by doing some expanding. Now, when we have a binomial times a binomial, which is what we're dealing with in the warm-up, many of you choose to use FOIL, first, outer, inner, last. And I'm going to start off by using FOIL for the first part of the warm-up. So we have x plus 2 times x minus 2. I'm not going to go through in as much detail what's happening here for every example, but as a warm-up, I'm going to spend a little more time on this. When we talk about first, that's the x times the x, which will be x squared. When we talk about outer, it's going to be the product. It's going to be the product of these two, which is x multiplied by negative 2. And that gives us negative 2x. The inner, of course, is the product of these two terms, which is 2 times x. And that's positive 2x. And then last, of course, is the product of the 2 and the negative 2 in this example. And 2 times negative 2 is negative 4. And then you simplify. And you always simplify when you have these situations by adding together the outer and the inner. And in this particular case, you get 0x. Negative 2x plus 2x is no x. We don't need to write no x. We don't need to write 0x. We can just summarize our answer by saying it's x squared minus 4. So that's the expansion of x plus 2 times x minus 2. Now, some of you don't like to use FOIL, and the more of you that I talk to in the building, the more I realize that many of you prefer this other kind of method. You simply do the following. You say, I have to multiply x by x, and you draw an arc there. So I'm going to use this other method for b, and you get x squared. Then you say, I have to multiply this x by the 5, and that's 5x. Then you go down on the bottom and you write negative 5 times x, which is negative 5x. And you take negative 5 times 5, which is negative 25. And again, these two terms add together to give nothing in this example. They don't always add together to give nothing. We've had many examples where they don't. So these examples are special. What we're left with is x squared minus 25. Whether you use FOIL, and I should have put here something. I'm just looking at what I wrote. This is nothing. Negative 2x and 2x is nothing. 5x minus 5x is nothing. So what we are left with is just x squared minus 4 and x squared minus 25. Whether you use FOIL or this kind of drawing of the arcs, it won't matter. I know at least 2 of you that are enrolled in this course don't really use either. You just look at the thing and you say, well, 2a times 2a is 4a squared. My outer, I think outer, is 2a times 7, which is 14a. My inner is negative 7 times 2a, which is negative 14a. And my last is going to be negative 7 times positive 7, which will give me negative 49. So minus 49. And again, those two middle terms are what I call a wash. They cancel each other out, and we're left with 4a squared minus 49. And if, as a student, you're watching this and you're writing this down, you're going, wait a minute, there's something that's happening in all of these, and it's the same thing that's happening in all of these, then you're getting the point. By the way, that looks almost like 49 squared that I wrote there. That is an a, not a 9. It's 4a squared minus 49. So if you're sitting there going, wait a minute, hang on a second here, there's something unique happening in each of these cases. It's the same thing in each. Then you're starting to pick up my point. Take a look at the next one, 6 minus h times 6 plus h. Well, 6 times 6 is 36. 6 times the h, so I've done this one, now I'm doing this one. 6 times h is 6h. Negative h times 6 is negative 6h. And then the negative h times h is negative h squared. When you add everything together, those two middle terms, as I say, are a wash. They cancel. So what I'm left with is 36 minus h squared. We do this one, the next one, 2x times 2x is 4 times x squared. I have to take 2x times negative y, which is negative 2xy. That's my first and my outer. Now my inner is positive 2xy, and my last is negative y squared. So what do we get? You get 4x squared minus y squared. You may look at f and go, what the heck is going on there? But I just want to remind you of something that I've told some of you before. When you look at what the language of mathematics involves, it's all about squiggles on paper. And those squiggles represent something. This particular squiggle represents 4 of something. This particular squiggle represents a variable which we call x. So it doesn't matter what we write on paper. These are all symbols. And if I FOIL this out, I have to take duck times duck, which will be duck squared. I have to take duck times frog, which is positive duck frog. What does that mean? cares what it means? It means duck times frog. I need to take negative frog times duck, which is negative duck frog. And then I have to multiply negative frog by positive frog. That gives me negative frog squared. And when we add these together, the two middle terms cancel, and you're left with duck squared minus frog squared. That's the first part of the warm-up. The second part is saying, what do you notice about the two binomials in each example? The two binomials are of the following form. We're talking here about, I'll show them to you, pair at a time. The question is, what do we notice about these two binomials we're multiplying? It's the same thing that we notice about these two. It's the same thing that we notice about these two. What do we notice about these pairs of binomials? Well, they're identical, except one of them has the first term plus the second, and the other one has the first term minus the second. So, the binomials, we can write it this way. The two binomials being multiplied are of the form something plus something and that same something minus the other something. They all look like this. And it doesn't matter if we call them A minus B and A plus B. In other words, it doesn't matter which comes first. These things are very special binomials in relation to each other. This and this are called conjugates of each other. They're actually called binomial conjugates, but for today I'm just going to call them conjugates. So going back and looking at A, x plus 2 and x minus 2 are conjugates of each other. When you look at B, x minus 5 and x plus 5 are conjugates of each other. C, 2a minus 7 is the conjugate of 2a plus 7, and 2a plus 7 is the conjugate of 2a minus 7. Duck minus frog and duck plus frog, those two binomials are conjugates of each other. So that's the first thing that we notice, is that the two binomials we're multiplying are conjugates. What is special about the product? So now what we're asked about is the following. What is unique or special about what we get? Well, in all of these cases, the outer and inner terms cancel because one's positive and one's equal. And what we notice is we only end up with two terms. If I highlight the answers here, we get two terms. We get two terms. We get two terms. And we get a difference of them. So it's 36 minus h squared. It's 4x squared minus y squared. It's duck squared minus frog squared. And we notice something else. And this starts to pile up in terms of what we're learning, but I'm going to go back and talk about A here. the x squared minus 4, both of those terms are perfect squares. What does that mean? It means 4 is a perfect square because it's exactly equal to 2 squared. I'm going to just indicate a few things here rather than point, because if I point, you won't see me pointing. This number is a perfect square. It is 2 squared. This thing is a perfect square. It is x squared. Over here, this is x squared. It's something squared. This is 5 squared. What about the 49? The 49 is 7 squared. What about the 4a squared? 4a squared is 2a squared. If I square 2a, I square the 2, and I square the a. When I take a look at this one, this is 6 squared. This is h squared. This is 2x squared. This is y squared. Obviously, duck squared and frog squared are both squares. But now comes the interesting part. Well, I'm going to hold off on that. So let's just write down our observations here. What do we notice about the products? We get a difference. They are a difference of 2 perfect squares. And now I want to add one more thing that hopefully ties everything together. And I'm going to pick one of the previous examples and I'm going to write it over here so I don't have to keep flipping back. One of the examples was 6 plus h times 6 minus h. And we got 36 minus h squared. So where did the 36 come from? Well, it came from the 6 times the 6. So when we multiply these two numbers together, it gives us the 36. Where does the h squared come from? Well, it comes from these two things being multiplied together. We get negative h squared. So the product is a difference of squares of the original numbers in the binomials. How is this useful? Well, x squared minus 9 is a difference of squares, which means we can write it as a product of conjugates. This is what we're learning from the warm-up. And this has to be x and this has to be x to multiply to give us the x squared. These two things have to multiply to give us the negative 9, and one is going to be plus 3 and one is going to be minus 3 because we've learned from the warm-up that the product of conjugates gives you the difference of squares. So x squared minus 9 factors into x plus 3, x minus 3. Once you get the hang of this, it's really quite simple. Everything leading up to number 4 here is just trying to explain to you, a student, why this works. You don't need to understand why it works, I suppose. You could take a look at 4b and say, well, if it's t squared minus 100, I guess I need a t here and a t here, and it's plus 10 and minus 10, and not worry about why it works that way. A squared minus b squared, well, it's going to factor into two conjugates. One of them will have a, the other will have a, obviously. They both will have a b, because conjugates have the same things added or subtracted, but one will be plus and one will be minus. By the way, it doesn't matter the order in which I write these. So for example, in B, I could have written t minus 10 multiplied by t plus 10. That's really the lesson. Let me summarize things and then we'll burn through a bunch of examples together. In factoring a difference of squares, there will always be two terms. This is how we recognize it. There must be a subtraction sign between the two terms, and both terms must be perfect squares. So for example, p squared minus 81 is a difference of squares because there's two terms, p squared and 81. There's a subtraction sign between them, which means it's a difference of them, and they're both perfect squares. What is p squared the perfect square of? Listen carefully, because I'm just giving you an additional example here. What is this a perfect square of? Well, the answer is p, so you put a p here and here. Is 81 a perfect square? Yes. What is 81 the perfect square of? 9. And then you go plus and minus. If I had 16r squared minus 9, there are two terms. We are subtracting them, and they are both perfect squares. 16r squared is the perfect square of 4r. 9 is the perfect square of 3, plus or minus. So in general, a difference of squares is something squared minus something squared. In this case, I'm choosing to use a squared minus b squared, and it factors into a plus b, a minus b. Once again, this is not difficult once you get the hang of it. The particularly difficult part sometimes for some students is recognizing if it is a difference of squares. Well, one way to look at it is, can I put something here and here that multiplies to give that 1, but it has to be the same thing? And the answer is yes, 1. So 1 is a perfect square of 1. Can I put something here and here, so I'm putting the same thing here as I am here, that multiply to give 9x squared? The answer is yes, 3x and 3x. So 9x squared is the perfect square of 3x, because 3x multiplied by 3x is 9x squared. And you put a plus and a minus. There's not much teaching that I can do here. It's just a matter of recognizing what perfect squares are and knowing that the pattern of factoring is to multiply the conjugates. All right, well, this is a difference of squares. What do I put in the first position of each that multiplies to give 25p squared? 5 times p. In other words, everyone, 25p squared is the perfect square of 5p. It's going to be plus and minus. What is the perfect square, 16q squared, the perfect square of? Well, it's 4p. 4q rather. 4q and 4q. And we're done. You could feel free to FOIL any of these out if you like, but it will work. Well, neither of these is a perfect square, but I've reminded you a couple of times to always look for a greatest common factor first, which is 3. You can check your calculator. 3 divides into 192. I can factor the 3 out and be left with x squared. I'll give you a second to take your calculator and divide 192 by 3 and convince yourself that you get 64. And now the x squared minus 64 is a difference of squares. It will be x plus 8 and x minus 8. For 36y squared minus 25, well, that will be 6y plus 5. and 6y minus 5. Because when you take 6y and square it, you get 36y squared, and 5 squared is 25. X to the 4 minus 81. Well, x to the 4 is the perfect square of x squared. In other words, x squared squared gives you x to the 4. So I can factor this into x squared plus 9, which is the square root of 81, and x squared minus 9. And here's where some students will stop, but just like this was a difference of squares, this is also a difference of squares. So I can factor further. I can't factor the x squared plus 9, but the x squared minus 9 factors into x plus 3, x minus 3. And we're done. I think we have one last example. No, two more examples. This term is a perfect square. So is this term a perfect square? So it's going to factor into something plus something, and that same thing minus something. I'll start with the yellow part. X squared is the perfect square of x. Now the blue part. And many of you will see this right away, but some people it takes a lot of thought to understand what it is I'm about to say. X plus 2 quantity squared is a perfect square of x plus 2. I mean, just to go off script for a second here, if I tell you that 9 is a perfect square, of 3, that should totally make sense. And all it means is when I square 3, I get 9. When I square this thing, I get that. Well, if you just look a little bit below that, what I'm saying here is if we square this thing, you get that. X plus 2 is what you square to get x plus 2 squared. And that means we put x plus 2 here, and we put x plus 2 here, and we clean this up a bit. We've got 1x plus 1x in here, which is 2x plus the 2. And over here you have 1x minus 1x, which is nothing. We're just left with the 2 in there. We're asked to factor completely, so when I look at this binomial, there is a common factor of 2 that I can factor out and be left with x plus 1. I still have this other 2 hanging around in the back there, and now I can multiply these two 2's together and just write 4 times x plus 1. So that's the answer. One final example, x squared over 9 minus 1 over 16. Well, it's a difference of squares. What do you square to get 1/16? 1/4, because 1 squared gives you 1 on the top and 4 squared gives you 16 on the bottom. What do you square to get x squared over 9? X over 3. Because x times x on the top gives you x squared. 3 times 3 on the bottom gives you 9. 1 is a plus and 1 is a minus. So there are some practice questions for you dealing with factoring differences of squares. I hope that lesson made sense to you. You might have to watch it a second time. Don't forget, just like anything else in this course, the way it seems lately anyway, what you need to do is you need to go slow to begin with until you gain the confidence and the skill that will move you forward a little quicker. So, in the meantime, have a great rest of the day and good luck with your math, and I hope to see you in school very soon. Take care.